Hello all. Let me extend a warm welcome to this session. I know it's a Saturday, but a lot of people have joined. That shows the interest in this hot topic. And thank you all for joining. Good morning and good evening to you all. I'm actually going to cover received some questions. So I'm going to answer those questions as we go along, as well as at the end. And you can also send me your questions during this session. I'll try to answer them to the extent possible. As you know, these are all very cutting edge and new age technologies. So the understanding gets only better. So I just want to make every minute of yours very worthwhile as you are here. So I'll get started straight away. So basically, people who have joined this session are like, what is in it for me? How is it going to help my job? What am I going to learn from this session? So these are the key takeaways. So we'll take a look at the AI. How has it evolved over decades so far? Or where is it now? What is its current state? And then we look at the foundation models, LxMs, as generally they are called, that is LLMs, LAMs, LRMs, and so on, and what their limitations are. Then that should give us, a nice sequence into the world models, what they are. So we'll introduce the world models in terms of, how they are different from the foundation. Basically, there are foundation models as well for world models. So probably it's not the correct term to say the foundation models are different from world models. Different people call the world models as world foundation models or foundation world models. So we'll use the word, the term world models. And then for the erstwhile or the current technology, mostly LxMs. Okay. Then after we introduce that concept and how they are different and their architecture, then we look at the real world examples who have come up with them, and of what they're doing with their platforms, who are the leading players, and how they are evolving. Then finally, we look at the applications of world models. So there are plethora of applications, but we cover a few of them. I'll take a little bit of a very a detailed look into some of the use cases as well. Then we summarize, answer some of the questions, and then conclude. Hope that's fine. So we'll get started with the evolution of AI. As you can see, it's been going on for decades. So 1950s to 80s, it was called symbolic AI. It's an old-fashioned AI. And those days, whoever have studied, that is the age of 80s, that decade, they probably would have done their research and PhDs in expert systems. So the expert systems are like, they're rule-based systems. You have to explicitly code those rules for the systems to work. So the programmer or the experienced programmers sit with the experts, the domain experts, understand what's needed, and then they actually code those rules, the business rules, into the system, and the system works fine. Then in the 80s and 2010, all the way to 2010, the machine learning started taking place. Basically, it's a data-driven approach. There are no, you don't have to explicitly program the system. And you feed the data, it learns from the data, it understands, and then it starts, taking actions. So it's a lot easier in the sense that you don't have to explicitly program. So you can, drive it through data, but it also has its own challenges. So one big difference is that the erstwhile or the earlier one is a very deterministic thing. So the program's output of the old-fashioned AI is deterministic, like any other program. But these data-driven approach, machine learning or deep learning kind of outputs or AI output is probabilistic. So there is one question in terms of, how accurate are these things? Is they're correct, they're accurate, but they can also hallucinate. So because they're not deterministic, we can't say that they're 100% accurate, but they serve the purpose. So if you look at human interactions and natural language, you really can't say, a lot of descriptive and subjective answers as, accurate or not. So it's in that realm. Then from 2010 onwards, there is renaissance of neural networks. Neural networks came into being based on mimicking the brain. So we learned from the nature how the nature has architected all these systems, how a bird flies, or how a brain's neurons work, and then from there the neural networks are derived. So these were existing even before. So that's why we call it as renaissance. So they came back as the computers became more and more capable, and that's when the modern AI is born. So from then on to all the way to current year 2025, these things actually drove the whole development and all the advances. Now, late 2010, that is something like 2017 onwards to present, there is a lot of generative AI that was deployed there, that was developed, and then there were significant breakthroughs in that, mainly through LLMs, large language models. And the way they evolved is like they kind of started, generating a lot of natural language, natural looking text, which is grammatically correct, which is making sense, which is more meaningful and all that. So encouraged by that, these were fed with huge sets of data and they were trained. And then okay, you have these large foundational models which came in, and then they actually put the AI into the realm of reality. Till then, it was like it was hypothetical, or there was a lot of AI washing. People were really looking at whether these use cases can be met or not, and how good they are. But this was one which actually gave a lot of impetus, and then it was a huge proof point. And that's when it took off like anything. And then you can see them like they are generating use cases, they're generating code, they're generating text, they're generating a lot of content, articles, summarize what you have read, answer your questions. It's not like a keyword search. It's so much of a conversational AI. Then there is the agentic AI. The agentic AI are autonomous agents where they can actually maintain the autonomy and complete a task. So they can take their decisions based on data and kind of result set, and then they can take dynamically. They can move around and then do those things. So that's the hot point of it. Okay, so let me just actually kind of switch off my video so that you get the better audio. Okay, so let's continue. Now, this is when it started in 2018. Then subsequently, a lot of versions came in, and then we can see it better. And then you can actually see how they resulted at. Now, going forward in future, there is a new lease for digital twins. So, what are these digital twins? They're not the picture on the right side, or sorry, on the left side, but it's like a digital virtual representation of a real life, a real world entity. It could be an oil rig, it could be a refinery, it could be a factory, it could be or any system. It could be a building, and that will have a kind of a digital replica, and then you can use that in the virtual world on your computer systems to actually simulate a lot of uh, scenarios, and then use that for your development. So that's very useful because you don't have to really deal with the physical world. And why we say that there's a new lease for these digital twins is like earlier they took place, but they're actually getting a lot better now. So we'll come back to this when we talk about world models. So they actually kind of form kind of bedrock for the world models. Then we are in the midst of world models. The early models have come in, and then there are platforms that are released to develop these world models, and then they are actually getting better at it. So there's a lot of investment that's going on. So the investments are very important because if you look at this whole evolution of AI, the way it came up, there were winters earlier, the AI winters between 1974 to 80, as well as 1987 to 93. That was driven by a lot of hype and a lot of unreasonable or like inflated expectations. When they haven't met, the funding started drying up. That's when the AI winters came in, and then of course the real world caught up with it, and then it started working better. Then in order to, these are all very huge, and heavy systems. They require a lot of training, a lot of compute power. And there is always quest for learning to learn better. If you look at how human beings or animals learn, how a bird learns to fly, how animals try to hunt or run, or how human beings do a plethora of things with very little training in comparison, with a lot of sparse data, there's a lot of scope for this field. So people are looking at this meta learning so that these systems can become better and better, so that you don't have to throw so much of data and so much of computational power. Then there is this quest for artificial general intelligence as well as artificial superintelligence. Now, there is one view, or there are multiple people saying that what has got us so far will not get us to these things such as AGI and ASI. That's why these LLMs have to evolve. And world models are probably a way to look at the physical AI or make things work in real world, not just the language related aspects of it. Okay, so with that, let's take a dive into the foundation models. These foundation models are large, deep learning neural network models. And they are like the architecture is like there are multiple layers. They are trained on massive, diverse. The good thing is the data sets can be unlabeled. It's unsupervised. You won't have to label the whole data. That's how it is. Otherwise, these things are not possible. Then a single pre-trained model, such as an LLM, can serve a very versatile functionality. Like you're already seeing, they're replacing search. So you can ask, you can prompt, you can give a very precise question and you get a precise answer. You get a very descriptive answer. You can ask it to, tone it in such a way that explain to me like a layman, or write this as a kind of, you write an article, write it in a professional manner, help me write my emails, my communication. It can help me make my presentations and so on. So that's the versatility of this. So they're just not kind of, in essence, they just predict then what is in the sequence, what is the next best word. But that functionality is so versatile that we can do all these things. Now, these foundation models, the term was coined and popularized by Stanford Institute for human-centered artificial intelligence, and it's kind of taken off, and it's so popular now. Basically, it's a learning algorithm, and when you throw a data set at it, of course, people have given whole worlds, whatever is available in the universe, whatever is available in the whole web, plus a lot of other things, and then people are also generating synthetic data and throwing at it, and it returns a prediction function relating the input to output. So whatever text you are given, whatever text that comes out of it in the generative form. And they learn general principles. So you don't have to really, the way we talked about rule-based programming, you don't have to explicitly program. So when you feed a lot of text, they understand the grammar, they understand the general principle well, and then they apply it across many related tasks. And that's why they are called foundational models. And these foundation models, that's how they became the bedrock, and then they had a starting point. And they have profoundly influenced the approach to developing and deploying AI systems. Basically, these systems are very risky. They cost a lot. And because of the probabilistic output, it's not very deterministic. You don't know upfront if you can do well or not, whether the system is going to work or not. So the uncertainty is rather high, but that's tamed with all this hard work over the years. Okay. Now let's look at the architecture of these foundation models. The key thing is the attention is all you need. The Google's paper in 2017, which actually made this possible. That's the transformer architecture at the center of it. Basically, what it came up with is self-attention mechanism that comprehends the contextual relationships within the sequential data. So, for example, if there's a word called bank, it could be a commercial bank which deals with money, which lends you money where you can, go and deposit your money, versus a river bank. And it can understand the contextual meaning of these words very well. And these transformers enabled significant parallel processing. So before this, people were using RNNs, recurrent neural networks, and also LSTMs, long short-term memory algorithms. But they were sequential in the sense that they do layer by layer, or they go from one end to the other, and they're not parallel. Now, with transformers, you can have multi-head attention, and you can give your attention to multiple parallel heads at the same time. And each of that can be on its own learning path, learning different projections of these input queries. Basically, it's called queries, keys, and values. There is a set as a data set. And the whole thing, because it's parallel, you can deploy huge number of GPUs or TPUs. So that's why people have gone to like thousands and thousands of these GPUs. For example, for XAI, Grok, they used 100,000 in the first phase, and then they expanded it to or 200,000 very quickly, and then they deployed and they trained the engine. So actually, these models are so heavy, they require, they're getting into billions of parameters, hundreds of billions of parameters, they're touching trillions of parameters, and they require huge computational input in terms of thousands of GPUs and TPUs. By the way, when compared to CPU, the GPU is more expensive and require a ton of them. And these foundation models or these LLMs have encoder-decoder stacks. Basically, there's an encoder and there's a decoder, which are stacked up. So the inputs go up the stack and come down the stack. So with each layer incorporating a multi-head self-attention mechanism for a specific one. And all these layers are fully connected. There is much of a technical detail. So I will not increase the cognitive load of this kind of session because we have mixed audience. But that's basically the architecture of foundation models. So the key takeaways are the breakthroughs that came in enabled this kind of thing, where even if you actually spend a lot of money, a lot of energy, it takes megawatts of power to actually train these LLMs, these models, but it still makes it possible, and they're so good. Okay, so here we'll look at the LLMs and their evolution. Now, I'm not going to walk through every line here, but I would like to point out a few patterns. Now, before, like I said, this 2018, 19, and 20 breakthrough of GPT, it was like, AI, there was a lot of AI washing in the industry. Basically, what's the difference between AI and AI washing? It's kind of, one is a breakthrough, as a joke goes, the other one is a marketing breakthrough. So we kind of attach AI to every advertisement word that you put out there, though it may not be really AI in that sense. But with 2019 and 20, if you recollect, the core concept, like the Turing test, Alan Turing was the one who gave many decades ago. He said that if you have two rooms, and in one room there's a human being, and in another room you have a system, and you don't know which room has what at home, and you start interacting with both of them. And as a human being, if you cannot really distinguish which room has got a human being and which room has got a system, then that system has achieved or passed the Turing test. That was basically the Turing test. Now, these GPTs have passed it comfortably. So earlier, the chatbots were not that good, but with these massive parameters and huge data sets, they kind of surpassed. And people even ask these questions during their chats, like, are you real? Are you a human being? So they ask this, and then the chatbots are actually kind of, getting into a kind of identity crisis now. Okay, so with that, if you look at it, there's another observation. Those 3, 4 years or 5 years, if you look at it, the other players haven't caught up. In fact, GPT, the OpenAI was the pioneer in that. So that column starts much early on. Then the other columns have started, like people have started saying Google is behind the curve, and then they have to catch up. So they worked hard and then they caught up with it. So they had come up with Bard and Gemini and all those things, and then you have other columns coming up. So as we can see, probably I haven't put every other column, but I put significant columns here. But you can imagine these columns will only increase as we go forward. Okay. So these systems, or these models are getting better day by day, version by version. And I would say GPT-5, which has started to be even with much bigger capability. We will not talk about it because that gets into a speculative kind of space, but it's around the corner. It's expected any month from now onwards. So that's how these LLMs have evolved. And now it's a kind of, a good time to take a look at the LxMs. So now that we understand LLMs, which are basically language and knowledge models, you take the whole world's knowledge, keep it in one model, and it'll ask anything that's been there on Earth. So as human beings, if you have expertise, you have to go to multiple experts or multiple specialists to get that kind of, you get your questions answered. But here, one system or one model gives you everything that has. Then came up, however, they're language models. They cannot reason well. They cannot work on logic. So they started putting together these large reasoning models, the LLMs. They have the logic, and then they start solving the problems. They combine natural language interface. They understand your problem. They apply logic. They come up with kind of chain of thought or tree of thought kind of thing. And then they walk through that, and then they resolve the problem. They break down into smaller steps, which can be smaller tasks and smaller steps. Then it'll resolve the problem. Then you have large action models. This is where the agentic AI comes in. So you can interact, and then you can get the task executed by them. You can also deploy multiple agents. They can be working off the same LLM or multiple LLMs. In fact, in future, there can be specialized models behind these agents if they're going to work on specialized tasks. And then you orchestrate those agents as a kind of a layer on top of that. So the agents, as opposed to the erstwhile bots or erstwhile programming functions, are like the programming functions are very deterministic. They carry out a specific function. Here they're autonomous, they're intelligent. So if you look at the robotic process automation, the bots are like they execute routine tasks very well. But here, they kind of understand. It's not exact understanding or cognition in that sense, but they give you a sense of cognitive automation here, and they are like a kind of intelligent agents. Then LVMs, which are large vision models. Now we talked about so far only the language and the logic part of it, but these things deal with image and video, so they can recognize the pattern recognition. They can identify the objects. And they can generate based on prompts. If you want a certain kind of image, for example, the image on the left side, you can prompt it, and then you get that nice image. Or you can generate videos, and you can generate movies as well going forward. So then there is another aspect to these large vision models. In fact, they form the foundation for world models. As the models try to understand the world around them, the real world around them, this is where the large vision models come into kind of focus. Then LLMs, the large multimodal models. What these things do is they combine all the capabilities and all multimodalities. So they simultaneously, it's not just one by one, but they can deal with text, image, audio, and video. They can deal with, you can ask them questions in your voice, and you can converse with them in audio. And then similarly, you can also deal with video going. And all those capabilities are simultaneously existing. So we can prompt to generate a specific video or fine-tune a video that is generated and so on. So as you can see, in the last few years, a very small set of years, there's a lot of progress that has been made because of this exponential curve, the technologies, and a lot of investment that is coming in, and a lot of brain power and human talent chasing these things. Now, with that, we come to the limitations of LLMs. So while they can do a lot of stuff, there are also limitations for these LLMs. They're static in terms of their knowledge. So what does it mean? They're frozen after training. So if you remember, I think a couple of years ago, when you interact with a chatbot or these LLMs, they give you this, kind of stock answer saying, I'm trained up to so-and-so date, so-and-so month and year, and I can't answer your questions after that. I don't know what happened after that. So my knowledge ends there. It's a clear cutoff. Now they kind of very, cleverly overcame that. It's not that these things learn on the fly, but we'll talk about it a little bit here. They really don't have dynamic adaptation, but what they have done is they gave real-time browsing capability, so they can spawn these things, they can plan, they can do some launch simultaneous searches, get to a lot of links, and then study what's there in that link, and then simulate that, and then give you up-to-date answers. So that gives you a feeling that you can actually, they're not out of date, and they can answer you up to the kind of minute information. Now, there is this inference time. Inference time is when you ask a question, it infers the answer and gives you that. So there is something called inference time learning that is in context. So you might say, someone might ask a question, oh, there is inference time learning. So why do you say it is static? That's basically it's in context. In the sense, when you have a session, if you have asked a question, it'll remember what you asked, what it answered, and the kind of conversation it remembers up to that point. And then it kind of, answers you within that context. So it kind of, it's a short context. This context is getting extended in terms of tokens. Like it started with 16K, 32K, then 128K. Now there are 1 million tokens that it can hold in the context. It's fairly big and good, but it's not like human long-term memory. Okay, see, the human brain, what happens is every stimuli, every action, every incident, everything you learn from there and your neural weights gets adjusted in your brain. And that's a continuous adaptation. It's a continuous learning. And they're stored in kind of abstract form. Whereas when it comes to LLMs, it's ephemeral. So it's within the session or within that context. There's nothing like a long-term memory. We'll come back to that when we get to world models again, but that's how it is. Then they're good at correlation, they're good at pattern matching, pattern recognition, but they don't have good causal understanding. We'll again talk about it at the last point. They don't understand what caused it, how things are being caused, and so on. They don't learn the laws or rules well beyond what they've been doing right now. So they're good plausible generators versus they're not so good robots. Of course, you have chain of thought, tree of thoughts. It can take multiple paths simultaneously in parallel and then work out the best path. But these are kind of workarounds. This is not full dynamic adaptation. And they're prone to hallucination. If they don't answer, they don't know the answer, they can kind of cook up and then give you with the same confidence level that as if it's real. That versus as a human being, you expect or you do a lot of grounded predictions of future states. That's not there yet. And they don't have a memory of their own. So we discussed this about context again. So there is something like, for example, in order to maintain that in context learning, there was this, prompt stuffing. And then that is basically you feed the old answers or earlier conversations till the time you run out of the context window. And that's how you actually maintain the context. That's a kind of crude way of doing it to start with. Then they started doing context caching. It's better than that. Then there is context engineering that's going on now, which actually like how to abstract and maintain this context much better and in a much more computationally efficient manner. However, they still don't have their own memory. If you keep some knowledge, it's a knowledge base, it's kind of an external memory. You link it to a RAG or various other mechanisms, but they don't have a memory like we have, the humans have. So in brain, it's an interwoven memory. The memory and logic, they work together and it's abstracted and there's so many mechanisms around it. And then they're massively energy intensive. To train an LLM, you kind of, spend megawatts of energy, basically what a city spends. And they're, energy guzzlers. They get better, hopefully, but it's like, the processors are getting better, the GPUs are getting better, there are better models that are coming in, better architectures that are coming in. But if you look at what a human brain does in terms of its exaflop performance, it consumes only 20 watts. It's very difficult to say as a very precise figure, but that's the kind of range that it spends. It's still a kind of a lot of energy for its size. It's 2% of human body's mass, but it kind of consumes 20% of the energy, especially when you are involved in a lot of cognitive tasks or a serious game, or for example, the kind of cognitive sessions that you're having like this, or playing a chess game and so on. But still, they're very efficient. Now, we come to the last point. This is the most important thing. This is like the recent Harvard paper where it's given as a reference here below. By the way, whatever I referred, there is a slide with all the references, so you can take them back and then you can study them later at leisure if you haven't already. So these foundation models fail to develop inductive bias. So what does it mean? So what they have done is they went back a few years. If you look at historical, like 400 years, we go back, there were Kepler's predictions of planetary motion. So how the planets can move. So Kepler came up with that kind of model, and precisely whose planet is going to be where in future. Based on that, Newton derived his laws. So Newton's laws came in. So what these people did as an experiment was they gave these LLMs of foundation models a lot of universes, like 10,000 universes, gave all the emotions, fed them with the data with the hope, and basically they're testing if it can really develop those laws, like the way Newton came up with those laws, and they failed. So basically, they failed to develop this inductive bias. They stayed in the realm of very precise pattern recognition. So they're good at correlation, but they were not good at understanding the underlying world model. So that's the precise limitation for you to get to AGI or next level. So there can be more and more horsepower that can be thrown at these LLMs in terms of the data sets, the number of parameters. You can make it larger and larger, and it will get better and more nuanced. But basically, it is a kind of fundamental limitation. So with that, let's get into the world models and their applications. So what are these world models? Again, if you look at it around the same time as 2018, there is a paper by David Ha and Jorgen Schmidhuber, and they talked about these world models. Basically, they have a different architecture. It's a different paradigm of a real world representation. So it can explore, these world models can explore potential actions and consequences internally inside their models. So if you hit a ball, you know what kind of velocity or which direction it goes, what trajectory it takes. If there is a glass at the edge of the table, if you push it, it will fall down, it will break. You know that. If you pour milk or if you do something, you know how the milk gets spilled. So there are actions in real world, there are laws, there are gravitational laws, there are consequences to your actions, and there are states. So the state before that is like the milk was in the vessel and then later it's on the floor. Now, the world models try to understand these things. So they have this internal simulation and there's a kind of mental practice within the model. So you don't have to really teach them with the kind of real world experience. So if you have to teach a robot with a real practical kind of scenario for it to train and understand and get start doing those actions, it becomes very costly, and some of them are very dangerous, and some of them are not practical if you want to do the kind of mining or space kind of actions and tasks. So you can actually simulate those actions, and then that actually reduces the need for costly and time-consuming real-world experimentation and training. And these are again generative AI models. They learn internal simulations of the environments. They keep that model inside, and they use it for predicting next state or future states. So in that sense, they produce novel outputs. They predict the future environmental states, not just a kind of a point state, like this is what the trajectory that ball is going to take, but they can give a host of hypothetical scenarios based on your inputs. And that's very useful. Basically, it can predict a range of scenarios, a range of outcomes. And that's very helpful because you can actually again analyze them, and then you can take the best forward path. Okay. Now, with that intro, what are the characteristics of these world models? They have the representational learning. If you remember or recollect a specific incident, you kind of you precise, but not so precise again. For example, it's like a video goes through your mind, or if you have seen an image, or if you have seen a sculpture, a statue, you can actually recollect. Basically, it's a representational memory in your brain, but it's a kind of compressed. And basically, it's a sensory input that's taken, and these are high dimensional sensory inputs and a lot of data, and that is actually compressed because it's abstracted, and that's the way you do. Otherwise, you can't scale up, and that's why it's a representational learning. And from this, it extracts essential features from these complex inputs. Kind of, you can run lots of videos, millions of videos, and then it learns from those things. And then, for example, how the light, falls, how gravity works, how the fluid flows, and so on. And they possess the capability to forecast the future states of the environment. So what you give as an input is like you would have given the past inputs, past states and observations, and you give the past data, build the model, pre-train and train, then you fine tune it, and then you give the current and past observations. When you give the current observation and also action by the agents in terms of control signal, they come out with future states. This is what can be done. And that's very useful. So I'll show it in a kind of diagrammatic fashion as we go on, so that probably you can understand it better. And like I said, it's not just one action path. They simulate various action paths, and then they can determine the most effective course of action. So it's a kind of range of probabilities. For example, if you want to take a sports example, you can run many scenarios or war games and then see what's the best course of action. And they're generalized in the sense that you don't have to train these engines or models exactly the same action set. So you could have trained them well and a generalized well, and they generalize well so that they can learn with a very sparse data. For example, you would have trained them with millions of hours of videos, and then you actually apply it with a specific scenario with just few hundreds or few tens of videos, like hours of videos, like 60, 70, 100 hours of video. And then it can take on from there. And then that particular scenario, it can start, predicting and forecasting. So that's how it can handle new conditions without, even if they were not explicitly encountered during the training. So you can give that as a kind of current input, and then it can learn and it can, start predicting. So this is very useful because you don't have to extensively train them so much for every kind of activity out there. Now, we saw the architecture of the previous ones, but what is the architecture of these world models? There are three components. One is a vision model. That's why I said I will actually revisit that large vision model. So this vision model is responsible for perceiving the real world, the environment around it, and learn how it is represented. So basically, it uses architecture such as variational autoencoders or LxMs, recurrent state space models, and so on. So they take these high dimensional, basically high resolution images or video frames, high frame rate video frames. And then there is also, kind of pre-processing. For example, some of these platforms give you the ability, if there's no motion, if the video is stationary, just drop those frames. If there is blur, and then if it's not enough light, or if it's distorted. So there's so many things. So basically you clean it up and then you start applying, and then progressively you make it better and better, high quality one, and then you apply it for your training and then take it to the compressed latent space. And these things maintain a memory of past events. So one of the real example when I talk, I will again revisit this. So unlike the in context kind of scenario, they can actually, recollect or work based on the past events or past videos. And there is a memory model. So this is built into it. It's part of that architecture. This memory model learns the temporal, the time varying dynamics of the environment. And this time varying need not be a kind of fixed set. It can be a variable time. So the scale and all that can change. And even then it can learn those temporal dynamics of the environment. And then it performs the predictions reasonably. This is the one which actually makes that. And this part uses RNNs, or it uses transformer architecture, because again, you can see how the transformers have been, helping even for these things. They're often implemented with mixed density networks, which are called MDN RNNs. And this is for predicting a probability distribution of future states. So basically, when you predict a range of future states, You also get probability distribution along with it, basically how likely it is. That's again useful. So you can take the most likely path or you can vary the input and then see how the probability is changing. Again, these systems are probabilistic. They are not deterministic. So there's always some probability attached to it. It's not 100% probable, but they're good, reasonably good for your practical application. And then finally, there's a controller. This is basically a policy framework, a policy network. It's lightweight when compared to the other two. It leverages the world model's internal representation. And this is where you give the actions and you control the actions. And so it combines the other two things, combining all these three things, it takes the actions. So if a robot has to pick up, hold its fingers, lift an object from one place to another, all these things are done through this control. Okay. With that, let's look at some real world examples, notable examples of these world models. They already exist. So Google, as you can guess, Google, NVIDIA, and Meta, they have been first of the bat to actually come up with these models. DeepMind has been ahead of it. They came up with Dreamer V2 and then V3. The 4 represents the reference. And then they also have Genie 2 as a kind of a foundational model. Then NVIDIA has a platform. So they call it Cosmos. It's a world foundational model. And they enable, other people who want to use it for autonomous vehicles or robotics and a whole host of other actions, they can use it as a platform to use their data sets and come out with the models for training. Again, it's based on CUDA and GPUs and so on. It builds on their earlier architecture. Then there is Meta's VJPA 2. There was VJPA 1 earlier. Now there is VJPA 2. So we take a look at them, each one of these things in detail. Now, Google DeepMind, basically Dreamer V3 is a general and highly scalable reinforcement learning. Basically, reinforcement learning means you have a reward system, and it's an algorithm developed by Google DeepMind and University of Toronto. So it learns from the world model. It learns its world model from experiences that are thrown at it. And for its success, there's something called an action critic policy. So its policy engine, lightweight policy engine, is based on actor and critic. So the actor comes up with all these predicted paths and scenarios or range of outcomes or predicted outputs. And the critic actually takes a look at them and then see which is the best path to take. So and they kind of work in conjunction, and then this actor critic policy makes it so better. And if you look at it, how it performed, one example is like without giving human data. If you look at previous models or how these machines have beaten people in the game of chess or Go or whatever. For this game, without human data or curricula, this was very successful in autonomously learning and mining the diamonds in Minecraft, which is a kind of very complex game. So with very sparse input, they say like one GPU working for 9 days as opposed to hundreds of GPUs working for multiple sub-days. So they could actually cut down a lot of computational overhead, and then they can kind of come up with this model which can work very well. And then, of course, there are ongoing improvements for these things. Then there is Genie 2. This is a large-scale foundational world model. So you see the word foundation again here. So they use it interchangeably, like world foundational models or foundation world models. And it can generate a vast variety of rich 3D worlds. So Genie 1 was a 2D maker. So it was predicting and coming up with those scenarios, the 2D world. It was rich, of course, but 3D is an extra dimension, and its real world is 3-dimensional. And it can simulate virtual worlds. So you don't have to work always in the real world. You can train it and then take the real world laws and rules and then take it to the scenarios, and then it can mentally train. It can come up with the simulation, and then you can train it in virtual world. It can generate diverse trajectories, the way we talked about the characteristics of these world models. And then it can generate counterfactual experiences. Means these experiences are not real. They're kind of just predicted paths, predicted scenarios. And they can be used. They're almost real. So that's why it's called an experience, but it is counterfactual in the sense it's not really real. You don't have to really put it in a real world to train. So that's how you can train those agents much more cost effectively. And here we come. It has long horizon memory. So what we mean by long horizon memory, it's not an in context stuff. If it has seen some videos, it can remember them. Even if it has moved out of those things, once it starts observing them again, then it can start acting and it can start predicting. So it's like you can give various, different types of videos, and then it can go back and forth. So you can give one set of videos, and then you can see what's the next predicted path, how the future thing looks like. Then again, you can go back and then do something else, and then come back to this, and so on. So it actually memorizes or remembers these videos as opposed to LLMs. So that's one good thing. Now let's take a look at another example, which is NVIDIA's Cosmos. They call this as a world foundation model. It's a generative world foundation model. Basically, this is for physical AI, like your robots which can work, or autonomous vehicles which can work, or the pickup vehicles in a warehouse, or players in a real game, be it football, basketball, tennis, whatever. And basically, you can accelerate that physical AI. The AI is actually going in from natural language and conversational AI to physical AI world. So this particular platform is meant to accelerate that development. So obviously, the applications are for autonomous vehicles, robotics, and all that. We see some of those applications. And it has, because it's a platform, it has a lot of tools. So you can use it to generate synthetic data for your models, and you can post-train on it. So it comes pre-trained, and then you can post-train and fine-tune it. And there's obviously a policy engine. So the policy model you can initialize, and then you can evaluate how well it is working. And then, of course, you can fine-tune and improvise it. So, and it can also generate multi-views. Simultaneously, you can, like, for example, for a car, you can have like 6, 12 line cameras or whatever. And you will have multiple views. You have a front view, you have a rear view, you have a side view, and so on. So similarly, it can generate all of those views. So you give all those frames, you give all those feeds, it can generate multiple things. So basically what it works, the model at the center of it is like, this is your input at time t, x0, and you also give a control signal. You look at multiple things here, and then it will predict at t+1, how is it going to be, basically the future frame. So you give a current past frame and then text prompt, and you give current scenario. Then you can give other inputs such as robotic control or camera trajectory, how you're panning your camera, how you're zooming or zooming out. All that you can do, and then the world model generates your future frames, and then it gives you nice videos. And it can do it simultaneously for multiple views. Okay, so that's about this part. Then we'll take a look at the Meta's VJPA 2. So VJPA is an abbreviation, it's an acronym for Video Joint Embedding Predictive Architecture version 2. Again, this is a very state-of-the-art visual understanding and prediction model. Now, the most important thing, I think we have been saying this again and again, the idea is to generalize these models so that they're trained in one kind of scenarios, or whatever is the this set of your data that is already there. But when it goes to the real world, you can actually apply it for the scenarios that it hasn't come across. So novel output it can come up with without having resorted or to actually giving that input in the past. So that's called zero-shot robo control. So you can actually straight away put the robo in a new scenario, and it'll start performing well. You don't have to, or you shouldn't have had trained it for that environment. And this is a self-supervised world model. So it requires a supervised model, but basically it can self-supervise itself. And there's a two-phase training approach in order to come up with this. But is first they actually pre-train and train, and the encoder and decoders are pre-trained on self-supervised data. So they give something like, for example, VJPA 1, they gave, I think, 300, they tried 300 million parameters. Now the new one is 1.2 billion parameters or something like that. They gave the millions of video feeds or millions of hours of video feed, and they again further increased it so that it gets better and more nuanced for this particular version. And then once you have that, you fine tune it on a small amount of robo data, the specific application that you're going to take the robo to. And that's where you can apply it for new scenario. So those are the kind of, some of the examples of real world models and what the big guys are doing. They're investing a lot of money. There's a lot of talent chase now. They're picking up talent and people with multi millions of dollars of payouts, and there's going to be a huge talent crunch all the way, and it's going to percolate down because, as you can see, there's a lot of cognitive load for these systems, and it requires a lot of in-depth understanding. While systems make it easier for the end user, there's still a lot of work that goes into it, and then basically it requires a lot of reorientation, reskilling, and rethinking of the entire skill base of the world. So, what are the real world applications for these world models? Autonomous vehicles, needless to say. So they need to learn. See, if you hear, like going back 10 years ago, we have been hearing about these autonomous vehicles and they're getting better. They're releasing, Waymo is releasing it city by city. Or do you have level 5 autonomous vehicle which can kind of drive in any country, in any kind of chaotic traffic? They're not there yet. How long will it take? It'll still take significant amount of time as we see it. But these models actually help, and these improvements or these breakthroughs actually help in making it faster, making it realizable faster. So they need to learn the intricate traffic dynamics, varying road conditions, varying light conditions, and complex pedestrian and other vehicles' behavior, other drivers' behavior, and so on. They don't have to not only deal with uh, they have to deal with not only the other autonomous vehicles, they also have to deal with human drivers and so on. Robotics, obviously, the ability to simulate and learn without really taking it to a factory and train them in real world, that's going to be very costly. You have to set up the factories, or you need to have access to real factories. You don't need to do that, and it also is very expensive and dangerous because the errors can be very costly. So the ability to simulate and have the mental map and mental learning actually helps a lot. And then reinforcement learning and gaming. So you can use AI agents to predict game states. You can simulate various strategies, not just war games, not just sports and games. You can do a whole lot of things with this. Learn more efficiently from internal mental practice. If you look at these champions, or when we were getting trained, the coach was actually asking us to do three kinds of practices. One is a mental practice, how you hold a racket, how you actually, the specific strategy, how you serve, how you actually receive the serve, if you serve in a particular manner, what you need to expect, what are the surprise, and so on. So you do a mental practice. Then you do a shadow practice of your movements without actually playing. So even real world sports people actually go through this. And this it can do. These world models enable these things, these models to do it without actually getting into real world. Then it can be used for scientific discovery and medicine, for example, protein folding, design of various kinds of new materials, materials of certain strength, certain characteristics, certain brittleness, certain flexibility, certain malleability, so on. And you can come up with a whole host of those things. And also you can simulate long-term climate changes. If you look at the weather forecast, which was kind of deterministic forecast versus AI-based forecast, and then can you do a long period average and extend your horizon of forecast to years and decades. So typically now what you get is like a season to season, and then you get a forecast for today, a week, 15 days, a month, and so on. And as you go further into future, it kind of gets vague. Basically, that's a kind of confidence interval which stops dropping. But if you can simulate long-term climate changes or have more accurate predictions, even if your horizon is much longer, then it's very useful. So again, you can use that. You can use this for. Basically, what happens is these models can extend the autonomous duration. So if a human being is going to, concentrate and work for 1 hour, 2 hours, so most of these tasks, if it can get to that level, one is a PhD level kind of researcher where it can answer those questions and have that kind of understanding and knowledge and reasoning, and also sustain its autonomy in the given scenarios. So it's not like a short-term prediction, but multiple scenarios. It'll sustain through the entire period of that. Typically, they look at 1 or 2 hours as it stands today, and that's kind of a very good achievement. Then it's very useful for virtual environments and simulation. We talked about rigs, the digital twins, and so on. So in future, going forward, they're going to be a physical AI. There's a kind of physical factory, a real world factory, and then you will have a digital factory or a virtual factory. So if you want to really, simulate the production schedules or the various, your recipes, or how you're going to actually your IoT parameters of your factory floor, all those you can simulate without, doing a costly production runs, and then get the output and outcome. So that's going to be very useful because it brings down the cost for the real world. And then it's not just for factory floors or warehouses, it can be extended even for larger ones such as smart cities going forward. Now let's take one specific scenario here, for example, sports. I think this is more appealing for everyone after this heady session. So basically, these models can enable hypothetically a sophisticated virtual coaching. What a good coach does. He observes your game, he observes your opponent's games, how they're playing, what are their weaknesses, what are their strengths, what are your weaknesses, what are your strengths, what you need to. So the whole strategy of, that whether they're getting tired, and then, whether the response time is coming down. So you have to get a replacement into a team, or what are the team dynamics. So the coach actually deals with all those things, but they still don't have a very nuanced, specific data. For example, how someone is holding the grip of a bat, or how their stroke is, whether the angle of approach is correct, whether the swing is correct, whether the speed is correct, and so many other things. So these models can actually read them through a plethora of sensors and video inputs, and we can take a lot of health data or human data like the heart rate, the perspiration, so temperature, so many things. And then you can actually combine all those things, and then you can come out with scenarios. So essentially, in the computer, you're going to have a digital twin of the game, and then you can have advanced strategy and plan for the games. And then you can have virtual playbooks, and then have multiple scenarios. So you play offense, defense, a combination of that, or change your serves, then how to actually attack and the weakness of the other player, and so on. So basically, the whole game gets elevated. If you imagine both the players trying to use this with their kind of at the backdrop in their training and coaching sessions. And then there is a predictive player analysis. So if you look at most of the analysis, if you look at it, it's all past analysis. What they did, how they scored, what kind of goals they made, how they shot, all that stuff. But here it's like, for a given scenario, if this kind of teams are playing like this, then what is going to be the predictive outcome of this series, or this kind of match, or this kind of game, and so on. So you combine that with various scenarios, it can get really complicated, but it also helps you a lot. And then you can also use it for real-time analysis and correction of players' techniques. So you can take the video feeds, you can take all these real-time inputs, and then what they have been precisely going wrong, or how fast they can improve their technique. It's going to aid a lot. Similarly, basically, if they apply a wrong technique, or if they take a wrong turn, or if they are, the posture is wrong, their swing is wrong, they can have serious injuries. So the top form players, if they have serious injuries, how it can set them back. So it can be used for injury prevention, and it can also, go back and see what exactly happened during that injury, and then it will help you with the recovery, a faster recovery, and so on. And of course, drills and skills practice, and every player is different. Everyone's style is different. The game is very personal. So you adapt these models to specific personal, style, and it's kind of hyper personalization. So that's one kind of a deep dive into sports model. So with that, we come to the end of the session. I think in time we spent about an hour so far talking about these things. So these are all the various references, and you can pick them up. This session is recorded. You can always refer to it. We will upload that. So just to summarize, so the AI evolved. It has been evolving for decades, and it's really accelerating now. Earlier we had some AI winters. with the kind of investments and with the kind of impetus that is there, and governments are actually backing these things, and then everybody is so excited. So probably the future winters are far off, and the future looks bright. And LLMs, we have seen how they evolved. They're very useful now. They have so much of impact. They can generate code like, with single prompt, they can generate thousands of lines of code, working code. Of course, it has got its own pitfalls, and the way you work is entirely different now. And LxMs, they extend these capabilities further. So they're not restricted to just language. And many of these limitations are overcome for the physical AI and future with the world models. So basically, it's a paradigm shift. It's a new architecture, and it shows so much of significant promise. Obviously, will it take us to AGI and ASI? That's a different topic. But basically, it's altogether a different dimension for real world, a three-dimensional world, and a whole host of parameters in real world with sensory inputs. Then large players have already started releasing these world models. You have seen that. And with that imagination, the sky is the limit for these applications. So you can apply these world models for a whole host of scenarios. So it's kind of a real step up of the game of these things. Okay, so with that, I kind of get into the Q&A. I received a few questions, and I'll take a look at, if any of the questions have come in into the feed. So first, I will actually try to address the questions that came in into my when people have registered. So one question is how these world models are different from the other data models or LLMs. So like I explained, see, models have been there. If you look at the BI or DW models, they're kind of pretty data-driven models. There's like Snowflake model and all that stuff. Then you have these LLMs. Those models are billions of parameters, neural network models with weights attached to them. Then world models have got three different components, basically vision, memory, and control. So in that sense, these are model. These things are combining multiple things. And tomorrow we can expect much more multi-model kind of world models, because the real world has got so many dimensions and so many inputs. Then there was one question, it's a good question actually. What's the kind of research going on and what are the limitations on these things? Obviously, while they are making rapid strides, a lot of these things have got their own limitations. So like I talked about, we really can't mimic, even now, we can't mimic the brain, the human brain. It's quite a long way. They're hugely energy intensive. People are buying land, people are buying power plants. The countries are expanding their power generation capabilities. For example, if you look at the comments, the US, they say we have a few dozens of gigawatts that we have added in the last few years, last 2-3 years. Whereas look at China, they've added hundreds of gigawatts. And then the context is training these models and then operating them. So it's like who can actually have the edge in the new world? Because without these things, it's going to be very difficult. So that's one. Secondly, the architecture and how you can do it, and also the pitfalls. When these are powerful, if they fall in the hands of wrong people, then they can do wrong things. It can be very dangerous. Also, it's like it takes a lot of money, huge amounts of investment. If you look at the amount of GPUs that are needed, that is hundreds of thousands of GPUs, even countries cannot afford. Many countries cannot afford. So we need better architectures to do that. And it's like, it's kind of, that is the thing. Okay. So with that, I think those were the questions that I have kind of received. I'm just seeing the in live messages, and then let me take a look at if there are any questions. I don't think there are any questions so far. Let me just take a look at it. Just give me a second, please. I don't think there are any questions. Maybe if there are more, of course, we can always come back, or I can, we can have a follow-up on that. So I think you can unmute if you want to ask any question now and ask me. Otherwise, we will conclude this session. So that's what I would say.
Yeah, Banu, this is Sandeep.
Yeah, hi Sandeep.
Yeah, hi. This architecture of world models, you talked about vision model, memory model, and controller. Is it vaguely similar to the MVC architecture used in software, model view controller?
Yeah, it's a way to understand, but they're different in the sense that the vision model is quite elaborate. So it's not just a model view. There, the view refers to your GUI, how you
Yeah,
interact with the software system, the UI, UX, and those aspects here. And then, of course, you have a control what actions you take and what you get out of it. So input, a process, and output kind of paradigm there. But here,
yeah,
it's much more complex in the sense that these are real world 3D uh, models. The vision models are like what's behind, what's next to it, what's below that, what's above that, and then the lot of rules that need to be learned, how the light reflects, and when you go forward, when you pan, when you need to take a path, when you have to navigate the obstacles, it's quite complex in that sense. So yeah, probably it's like it's a kind of three-dimensional architecture, but this is different. It's a good
oh,
question.
yeah. Thank you.
Thank you all. I know that it's kind of Saturday and the time has been a bit odd. I know some people have joined from even what you call Singapore and all. It's kind of close to midnight. And thanks for good feedback. Thank you all. And see you again later. So we are recorded. We'll try to share this for those who have not attended or who want to refer to it in future. Good day and good night. Thank you, David. Thanks for joining from London. Bye.